Hey guys, chapter 21. This is the fourth video, wrapping up the last section of the PowerPoint. Just a little bit of general information about nuclear chemistry because people are often interested in it. In this section, if you kind of just pay attention to just the general information, don't worry too much about the details. There might be one or two multiple choice questions on the test from this part. So just information that's good to know. If we are measuring radioactivity, the most common device that's used is called a Geiger counter. Essentially, the idea is you have some radioactive material. When it gives off radiation, which can be different forms, alpha, beta, gamma, and so on, the particles will, as they flow into the probe, if they are charged particles, it will create a movement of electrons, just the attractive repulsive forces. And that movement of electrons is flow of electricity, which can be measured as a voltage. And based on the strength of that signal, they can measure how much radiation is coming out of the sample. So there are a lot of different units that can be used to describe radioactivity. In the example problem we did earlier, you can use becquerels to measure. There's also a unit called curies, Roentgens, and then probably the most common one that people see, REMs are radiation equivalent measurements. But that's probably the one that we see most commonly, especially in biological systems, where REM is an equivalent measurement for how much biological damage radiation can do. So, on a daily basis, the amount of radiation that we are exposed to, there are radioactive isotopes all around us. I mean, in the air, in countertops, in computers, in rocks. I mean, there are radioactive isotopes everywhere. Okay, on a daily basis, the average person is exposed to about 135 millirems of radiation. That's a pretty small amount. It does vary pretty widely based on where you live. Okay, some areas have higher concentration of radioactive isotopes than others. But let's just say you go in for an X-ray. If you get an X-ray, it does depend on what type of X-ray you're getting, but on average, one X-ray will give you about 20 to 200 millirems of radiation. Again, that's not that much, although the issue is if you get X-rays often or you have to get a lot of X-rays over a short period of time, that can be damaging. And even more important, like an X-ray technician, there's a really important reason that they put the button that the technician has to push to do an X-ray. It's in a separate room with a insulated wall in between, so that when the technician gets you set up for an X-ray, they have to leave the room, hit the button to do the X-ray, and then they come back to you. That way they're not getting those repeated doses of radiation, because radiation damage is additive. The more times you're exposed to it, the more damage it does to your body. Okay? If you have either cancer diagnosis or treatment, they have scans that they do. These are often, especially for treatment, where they're trying to kill cancer cells. It'll be a significantly higher dosage. 7,000 millirems is like 7 rems of radiation. That's a pretty good amount. But again, it's a pretty significant thing they're trying to do in killing cancer cells, and there are costs to that, so that's why it's so rough on your body, is the amount of radiation that you're being exposed to. If you live outside a nuclear power plant, they are shielded so well that actually the amount, if you're right outside a power plant, the amount of radiation you'd be exposed to on a daily basis is about 0.1 millirems. Tiny, tiny amount. Of course, that does assume that everything with the PowerPoint is working properly, and you don't have any kind of a leak or a meltdown or anything like that, which has happened a few times in history. So on average, a person can get somewhere between 1 and 170 millirems, but as I said, the average is about 135. The LD50. LD50 stands for the lethal dose for 50% of the population. So if 100 people are exposed to 500 rems of radiation, that would kill half the population. The other half, while they might survive, they would probably be very sick and develop a lot of other issues from that. But that's the LD50 for humans. But don't worry, if there is a nuclear holocaust, The insects will be able to take over because they can withstand 100,000 rems of radiation and still live. Some of this is based on their exoskeleton. Some of it is based on the fact that their genetic code is a lot simpler than ours is. All that, okay? And then also, along with the insects, you're going to have bacteria because they can withstand up to 50,000 rems of radiation themselves. All right, so what happens when you're exposed to radiation? Well, essentially, two things here. First of all, the type of radiation does matter. Alpha radiation, these are big particles. The helium nucleus is the largest type of radiation that we talked about. Since they're big, they move slower. It's a lot easier to stop them. So pretty much if this is your body tissue, the outer layer of skin right here, alpha particles very rarely will actually get through the outer layer of skin. So they stop. I mean, if you're exposed to alpha radiation, of course it can cause skin cancer and things like that, but not much internal damage. Okay? If you want to block alpha particles, honestly, if you just hold up a sheet of paper, that blocks alpha particles. Or if an alpha particle travels through the air, it doesn't usually travel more than a few inches before it bumps into some other molecules in the air. And then that would diffuse the energy, and it would just become a normal helium atom pretty quickly. Second type of radiation, beta particles, are smaller and lighter, and they move faster, so they penetrate more. They can penetrate a few inches into your tissues, your bodily tissues, so that can do a lot more damage. To block beta particles, you would need either a 1/4 inch of lead plating or a few inches of cement or concrete to do the job of blocking beta particles. And then finally, the most dangerous are gamma particles. This is high energy photons of light. They will pass through your entire body, through your bone and organs and everything. The only way to stop gamma particles, you would need either 4 inches of lead plating, which is 4 inches is a good bit, or an entire meter thick wall of concrete to block gamma radiation. When there have been nuclear meltdowns, Chernobyl, Fukushima, in those cases when they can't really contain the radiation or stop it in any way, they just bring in truckloads and truckloads of concrete, cover up the entire site with just meters and meters of concrete to keep all the radiation on the inside. So again, just idea of what the damage, if 0 to 25 rems of radiation doesn't cause any outward effect, although the cumulative effects over days and days can be significant. 25 to 50 can cause your white blood cell counts to go down. At 100 to 200 rems, you start to feel sick and have nausea and all that. And then, like we said, at 500 rems of radiation, within 30 days, half the population would be dead. All right, so last two things that we want to talk about just to make sure, with nuclear chemistry, you have to talk about what fission and fusion are, okay? So nuclear fission is an artificial process that basically we have a large atom, we're going to shoot it or bombard it with a smaller particle like a neutron. Imagine this is like taking a watermelon and shooting it with a rifle. When the bullet hits the watermelon, it's going to split it open. So I'm going to take the larger atom, I'm going to split it in two pieces. The two pieces I split it into are usually not going to be equal in size. Okay, it does split close to half and half, but not always. So in this example, I shoot a uranium-235 atom with a neutron. When it splits, I get krypton-91 and barium-142. Again, with conservation of mass, if I get these two atoms, that means that 3 neutrons would also shoot out. I should maintain my total mass. I should maintain my total atomic charge. And if you check the numbers, it does work out. Now, every time I shoot a watermelon with a bullet, the watermelon is going to split in a different way every time. Same thing applies with fission. The bottom reaction here, uranium-235 plus a neutron, if it splits to give barium and krypton, this is the reaction that's displayed up above. But then another fission that I could do could possibly give me different pieces that break out. So every uranium atom, when it splits, there are lots of variations for how it can split. Okay, but in each of them, you should always be able to maintain the mass balance and the charge balance for the reaction. Now, when we do nuclear fission, there are really two main purposes for doing nuclear fission. One is if we want to set off a nuclear bomb, which in the 1950, obviously World War II, and in the 50s, we were building fission bombs where we had uranium and plutonium. We would strike it with a neutron, and the atoms would split. When the atoms split, we start the reaction by having a fast-moving neutron strike a uranium atom. When we split, if we get 3 more neutrons coming out at high energy, if there are more uranium atoms around the first one, when they come out, if these 3 neutrons hit another uranium atom, then that's going to cause another reaction to occur. And then when it splits, if it hits another uranium atom, then that can cause that one to split, and so on. That's called a chain reaction. Okay? Now, 2 things have to happen in order to have a chain reaction. Number 1, we have to have enough uranium atoms around in close proximity with each other so that when one splits, the neutrons can hit another. And then the other thing we have to have when it splits, these neutrons are those are the pieces that kind of keep everything going. So this is what when we learn about nuclear enrichment of nuclear materials. Basically, they take rocks and minerals that exist in nature. They have some uranium in them, but it's very low concentration. When they enrich the uranium in those minerals, basically what they're doing is they're trying to get rid of the other elements, concentrate the uranium until it gets up to a certain level where the chain reaction is possible. Okay? If we can get above that, that's what corresponds to the critical mass, which allows for, if this reaction accelerates and gets bigger and bigger and bigger, that's where we have a nuclear explosion, which is what happens in a nuclear bomb. Or if we can maintain the reaction at a slow rate, just get the concentration of uranium high enough that some of the neutrons hit other uranium atoms, but not all of them, then that would be where we could establish a controlled fission reaction, which is what happens in a nuclear reactor. A nuclear reactor can be used to power a power plant to produce electricity for whatever area around it. The United States does have some nuclear power plants that are in service. We actually haven't built any new ones for probably 30 or 40 years, although there are new ones being built right now. There's actually one in Georgia not too far away that is way over budget and way behind schedule, but it should be opening in the next few years. There are countries like France where 75% of their electricity is produced by nuclear power plants. So a nuclear power plant basically looks like a regular power plant, where in a regular power plant we burn coal. When we burn coal, the heat that's produced is used to boil water. The steam that comes off the boiling water is used to turn the turbine, and then the turning of the turbine is used to create electricity. Okay? That's how a regular power plant works. In a nuclear power plant, the only thing that really changes is the source of energy. Instead of burning coal to produce the heat that we need to boil the water, we're going to perform a nuclear reaction in a reactor core. The energy that comes out heats up the water, and then everything else is the same. Okay? In order to keep things under control, you have to have uranium that's enriched up to a level that can maintain the chain reaction. And then if it gets going too fast, they have things called control rods stuck down in the reactor that if you get too many neutrons flying around in there, the control rods are an adsorbent material that will suck in all the neutrons and keep it from getting out of control. Graphite is one of the main materials that the control rods are made out of. And if we have a nuclear bomb, again, that's the general setup for it, but let's move on. Now, one of the issues with nuclear fission is that the materials that are produced are typically quite unstable. They are radioactive materials that have to be disposed of. You can't just put them in a normal dump, because then you'd have all the area around the dump would become radioactive, and it can't get into the water table, because if the radioactive materials get in the water table, again, that's going to spread it out to where people can be exposed to it. So what generally has to happen They have to find a region of the Earth's crust where it's very stable, so there can't be an area where there are a lot of earthquakes. You have to find an area where it's a stable rock formation with no water really close to it. They put the waste into like metal barrels or something like that, and they bury it, and it has to be stable for probably tens of thousands of years before the radioactive material kind of diffuses itself and it's no longer dangerous. So, last one, nuclear fusion. So, in the 1960s, we moved on from the bombs that we dropped in Japan in World War II were called atom bombs, which are fission bombs. They were pretty powerful, did major damage to the cities and places where they exploded. Now, in the 1960s, the Cold War between the United States and Russia, basically both countries were trying to develop the hydrogen bomb, which is a nuclear fusion bomb. Okay, so what I want to do with fusion is take two small nuclei, I want to crash them into each other at high energy and form a larger atom. Again, we saw an example of that earlier when we were artificially producing some of the big radioisotopes that exist at the bottom of the periodic table. But when we do nuclear fusion, the amount of energy for fission, which I didn't mention earlier, but essentially fission is on the order of several thousand times more energy efficient than burning coal. So if I burn 1 gram of uranium, I get as much energy from that as burning tons of coal. So it's a huge advantage energy-wise. Well, fusion is like 1,000 times more powerful than fission. Okay, so if we could actually harness nuclear fusion and use that in power plants, then a lot of our energy issues that we've had over the past 100 years would disappear. Now, one of our issues, though, to achieve nuclear fusion, we have to get two atoms and get them to, as they approach each other, the positive charge of the nuclei is going to make them repel. We have to have them moving at high enough speed that their momentum is going to make them crash into each other to overcome the repulsive forces. The amount of energy that's required for that, you have to get the temperature of the sample up over, I think that says 10 million degrees, which the only time you find a temperature that's nearly that high is inside a star. Actually, two places. It could be inside a star, or it could be inside a nuclear fission bomb. Okay? So typically, when we, in the 1960s, when we developed the hydrogen bomb, it's actually a combined bomb where there's the explosion is initiated by nuclear fission that produces enough energy to get the temperature up into the millions of degrees, which then allows fusion to occur, which is even more exothermic and causes an even bigger explosion. So, here's our reaction. We take two isotopes of hydrogen. This is the most common version of nuclear fusion that would be used in a nuclear bomb or a reactor. But it's going to be hydrogen 3, which is called tritium, reacting with hydrogen 2, which is called deuterium. You don't need to know those names. But hydrogen 3 plus hydrogen 2, they're going to react and combine to form a helium nucleus, or an alpha particle, and then a neutron comes off, and a huge amount of energy is released. Okay, now, what are the great things about this? Well, number one, the fuel for nuclear fusion is just hydrogen. Okay, we have all the hydrogen we need in the world if we just look at the water in the oceans, right? Plenty of hydrogen, even though tritium and deuterium are less common isotopes, if we can pull them out of the ocean, we have more than we could ever use. So we have unlimited fuel for nuclear fusion. The product of nuclear fusion is helium. Like I said, nucleus at first, but when it gains a couple electrons, it'll just end up being a helium atom, which is not dangerous. We can just release it into the atmosphere, and helium actually float into outer space. So basically, I have unlimited fuel. I'm not producing nuclear waste anymore, and I'm producing a much larger amount of energy than any other process that we know of. So nuclear fusion is what they call the holy grail of energy, where if we can actually harness this, and instead of just using it for bombs, if we can actually harness it, make it workable for reactors in a nuclear power plant, then all of our energy problems are solved. Okay, now, they are supposedly building a fusion reactor, I think, again, in France, although that project, again, every few years they update and say that they're still a few years away from finishing it up. So far that has not successfully been achieved. And that's the end. So on chapter 21, go through the videos, work the master in chemistry. Really, if you do that, that's the material that you're going to need for the test. The chapter goes into a lot of topics that I didn't talk about in the videos. If you're in my class or Dr. Nalibos' class, focus on what's in the videos. Make sure you can complete the homeworks. Don't worry about any topics that are not covered in one of those two places. Okay? Good luck to you.